Yeah, I guess we'll get started then. Today we have Arvind visiting from Minnesota. So Arvind is a PhD candidate in computer science at the University of Minnesota. And today he'll be talking about knowledge-guided encoder decoder frameworks for environmental modeling. So yeah, take it away.
Perfect. Everyone in the room can hear me, right? So yeah, as you was just talking about, so today I'll be talking about this advancing environmental modeling with knowledge-guided encoder decoder frameworks. First thing, just give me a moment. Okay, so text is being hidden there. Okay. Need to build robust personalized prediction models for a set of entities or tasks is applicable in lots of different domains. So to first, I would like to define what an entity is or what I mean by an entity. So what I'm trying to say is entity can be anything on which a driver is acting and it's showing a response to that particular thing. So for example, an entity could be a river basin or a catchment where you have a weather or something of that sort acting on it, and it's showing a stream flow in response to that particular weather. Or it could be things like, a location in the world where you have a flux tower in or something of that manner. You could have weather and LAI acting there to produce some sort of a GPP response in that place. We define effectively all these systems as entities. So effectively, you can think of that in that this particular abstract sense. You have some physical driver going into the system or acting on a system. You have some system characteristics and some state which the system has. The state may or may not be observed by some satellites, ground observations, and so on, and all of them together are producing some sort of a response. These processes may also be evolving at different timescales, effectively, or they may be evolving and interacting at different timescales. So you also want to model all of that. For example, soil moisture will be building up at much faster rate than snowpack, which would in effect affect how stream flow responds, how a basin would respond for a particular stream flow with a particular physical driver and so on. Uh, with that in mind, what are a couple of things we usually want to do when we model these things? Some of the things you usually want to do when you model any of these systems are you either want to extrapolate that in time. That is, you want to know what is going to happen in future if something else, a new input comes in or something of that sort in the same site. Or you want to probably extrapolate in space. You want to be like, okay, I have some observations in 10 different places. I have a new location, 11th location. How is the system going to behave there? Or you'd probably want to do both. So that is, you want to extrapolate in space and time and both. Um, but there is a fundamental limitation with physics-based models here, which is what you'll typically use for all these things. That is, if you look at the two axes here, you have an axis for entities where each row corresponds to an entity. You can think of them as locations or some patch in space for now. And you have a x-axis, which is time. So a fundamental limitation with, at least to an extent with physics-based model, is that you probably have to calibrate for each of these entities separately. You can't share the knowledge very effectively. And so what that means is anytime I want to make prediction of one of these rows in orange, I'll probably have to train that model in one of these rows in blue. The advantage which knowledge-guided machine learning or machine learning in general has is that you're probably going to share all your parameters in whatever you're training. That'll help you extrapolate or share knowledge to make better predictions in these kinds of different situations. For example, if your situation was to, let's say, predict, just do extrapolation in time, you would do something like multitask learning, where you'll treat all of these different sites as tasks, and you'll have a single model which will have a shared set of parameters between them, which you'll use to make predictions on all of these tasks. Or let's say you want to do extrapolation in space. You could do something as simple as zero-shot learning. For example, let's say you have hundreds of sites where you have lots of data and you've trained your model and everything. And let's say you go to a new site where the only thing you know about that site is things like what kind of soil it has, what kind of climate zone is it in, or what kind of ecoregion is it, and so on. Can we use that information, just that ecoregion, soil, or climate zone information, to transfer the knowledge across? If you can do that, that's an example of zero-shot learning. Or let's say you have some observations there. Maybe it's a site where you have sparse observations. Even very limited observations can do wonders for you. That is, you can use that limited observations along with the well-observed sites to make better predictions in those sites. And that is what we term as few-shot learning. And all of these different ML techniques in general can help you make significant predictions and extrapolation in time, space, and time, as opposed to a physics-based model where you had to calibrate these parameters individually. So with all of these in mind, traditionally, sorry, I forgot this. So these extrapolations, along with generalization to new tasks, are some of the things which you actually want to do with things like foundation models. And that's why foundation models are becoming really, really popular in most fields in general, especially after ChatGPT came in. Typically or traditionally in environmental ML, these problems are modeled as an X to Y approach. That is, you have a query. For now, you can think of query as just some sort of an input going into the system. And query is just typically the terms we use now. It's just an input going into the system. And you have the system producing an output to that particular input through some sort of a predictor model. Yes, this direct X to Y approach works. But what that often means is it's very limited in ability to how you can incorporate context and new knowledge. And oftentimes, one of the most used way of adding in context is just to do it in some sort of an autoregressive fashion, where you'll just take your output and you'll feed it back as an input along with your normal input to make a new forecast or something of that manner. The question is, can we do better? And the answer to that, or what I think the answer to that, is that you just use your standard encoder decoder approach. We've been doing encoder decoder like models in machine learning for more than a decade now. So what encoder decoder naturally is designed for utilizing context. So what do I mean by context? Context could be these things like historical drivers, historical response, simulations, characteristics, and so on. So what I mean by context is any information you have, which can help you make more structured or more effective prediction from query to response. So any information which helps you make a better query to response prediction is what we term as context here. Most oftentimes, it'll just be some past input and output in that site or characteristics of that site. And because you have structured it this way, you have a separate encoder and a decoder. You can handle variety of information as context, and it's much more well suited for sequence to sequence tasks, especially if you want to run this decoder in an autoregressive fashion or that sort manner. And because you're also separating this query and context, you can do a lot more things with this context processing and query processing. The first benefit is basically now you have additional avenues for knowledge guidance. Why do you have an additional avenue? The easiest thing is just that if you were doing just a single model from an input and output, and if you wanted to do something, for example, autoregressive, you would have had a decoder only model. So what that would mean is you probably are doing some sort of a causal modeling. If you're using RNNs or LSTM, you're just doing a causal modeling, or if you're using transformers, you're probably doing causal attention. So what that means is even if I want to feed the context in along with query, I'll have to do causal attention on that context. So by separating this, now I can even do bidirectional modeling if I want into the encoder, and I can process in the context in whatever fashion I want. The processing of that context could be knowledge guided. Another advantage is that because I'm encoding that into some sort of a latent space, I can do multi-scale processes better. And if you imagine that this context to be the state of the system, you can do data assimilation much more effectively. Another advantage is if I define a probability distribution over that latent space to effectively define how my predictions behave, I can also do a very principled uncertainty evaluation. And because the model is so flexible and you can handle different varieties of things, it's really, really suitable for foundation models. Yeah, go ahead.
Are you going to go into the uncertainty quantification? Does that fit into the encoder part?
Uncertainty quantification would be done on the latent space. So you'll define a probability distribution over this latent space. And by defining that, what we saw is you can do better than compared to things like base by backprop, dropouts, and so on. So it'll help you do it in a reasonably structured manner, let's say. Can I move on? Yeah, and elements of this approach, the encoder decoder thing, are already being used by lots of people. Some of the examples was one of our papers from about 2 years ago, and this is a very recent paper by Google, which was doing flood forecasting using a similar, let's say, encoder decoder approach or elements of it. So with that in mind, I was just talking about some benefits here in the previous slide. So we were trying to see if we can actually show those benefits, some of those benefits. So we have done multiple experiments or different let's say, papers over the time. The first one is we were trying to see if we can add additional avenues of knowledge guidance And we did that through prediction of GPP in sparsely observed or unobserved locations through a method called TAMRL. So each of these I'll be going into details in the next couple of slides. So I just wanted to briefly show what are the methods and what benefits we saw from them. For the multi-scale processing, we worked on a project called FHNN in collaboration with NOAA. We were able to see that we're able to do better operational streamflow forecasting by modeling multi-scale processes better, and we were able to do data assimilation better. For uncertainty quantification, we were able to see that we can better quantify uncertainty for streamflow compared to things like base by backprop and dropouts. That work was done in collaboration with USGS, and the last one is what I did mostly over my summer this year with ORNL. Was basically we were trying to build a backbone along these methods so that this backbone can in future be trained with a lot more data to make a foundation model, which is what I'm doing right now. For the first thing, so the idea behind the first paper, the STAMRL, is very simple. So we just talked about an encoder decoder approach. If you think about how a traditional physics-based model behaves, you have some model, you have some respective parameters for that, which you want to calibrate. And once you have those parameters, you probably are running that decoder or a forward model using that parameter. So what we were thinking is, can we have a coupled system of an inverse and a forward model? So all you're doing is in the first block, let's say you have an inverse process where you have an input and output. You're using them together to figure out what parameters the system should have. And then you're later using that system parameters along with the model parameters to make your final prediction through a decoder. That's all. It's pretty simple. So what we realize is what we are effectively doing is during training, you'll train both of these forward decoder and the inverse model encoder together on well-observed sites. So that once that's trained on well-observed sites, all you need is a few observations in a new site to effectively get the parameters for those sites. And since we have learned how to get these parameters across sites, you're sharing that knowledge to figure out how it will behave on the new site. And once you have that set of parameters, you can just use them to get your final output through a decoder. Excuse me. So this is what that architecture looks like. So it's pretty simple. The modulation network is our encoder. And this basically this blue part in the base network modulated one is what is our decoder. So all we are doing is you're feeding some input in. And as you can observe, it's a bidirectional thing. It's not really a causal modeling per se because we are not restricted. You get some sort of a parameter, and you're using that parameter to effectively modulate your forward model to give different outputs depending on what kind of characteristic that site has. We tested it on multiple things, some synthetic data set, streamflow, GPP, and so on. Here I'm just showing GPP. So this is daily GPP prediction on FluxNet. There was a paper here in LEAP about a year ago by Pierce Group and Juan called Metaflux, so where he was using MAML to make predictions for GPP. So we used the exact same testing sites as what he had before his whole data set was created. We saw that you can do significantly better on GPP predictions compared to traditional meta-learning approaches like MAML, multimodal MAML, and so on. We have a lot more other baselines in the paper. Here I'm just showing the closest approaches. And what we saw was we can do significantly better, usually 10 to 30% better. And the method is much more simple, and it's 10 times faster. So that showed us promise that it's indeed feasible. And then we thought like, okay, but the constraint here is that we needed limited information to make the prediction. And often for most sites in the world, you won't really have any observation. So we were trying to see if can we extend this method? Can we do something so that we can make an ungauged prediction on sites where you don't have any observations? So along that, we tried a very preliminary approach. So all we did is we had an encoder. The encoder, we were feeding an ecoregion, climate zones, lat long as some sort of a static feature. The model embeds that into some representation space and uses the same modulation network to make a prediction. Nothing fancy yet. And even by doing that really, really simple approach, without any observations, we were able to do pretty good on GPP and RECO on FluxNet. And we also compared those results with what was already reported in Metaflux as a whole data set in the first place. And even though Metaflux used data for those 17 sites to make predictions, we were still able to do equivalent or better to that, even without using any data from those sites. And for a completely independent perspective, we also tested our approach and what Metaflux predicted on Ameriflux, and the results were drastic there. So both of them in Ameriflux case did not have access to that few short of data there. Both of them are effectively acting independently as ungauged. And there we see more than 100% improvement. Actually, it's like about 70, 80, depending on which site you're working with. So this showed us promise that it's indeed possible. So we are now effectively working on a slightly more advanced method using that TAML's perspective to get and eventually a product out which can show GPT better. The next thing, so basically the conclusion is that you can incorporate knowledge better. And this is just one step forward showing us that you can indeed do it. For the next thing, we wanted to see, can we model these processes evolving and interacting at multiple temporal scales? So this was the work FHNN, which was done with NOAA Operational Forecasting Center. Again, the idea is the same. You have an encoder, you have some sort of a context going in, which in this case was historical weather and historical stream flow. And once you use, then you use your model to effectively get multiple one of these latent states. Here, what we are saying is, let's imagine the processes is evolving at different time scales. Let's just model those different time scales as latent states. And they'll be evolving latent states, and then you can use them together in a decoder model to make your final prediction. And so the basic idea was is that once you hierarchically factorize that, now you can have much more longer context, because typically these models have recency bias. And by now factorizing at different time scales, you mitigate that recency bias a little bit. And you also have a slightly small step forward on explainability, because you do know that the process evolves at different temporal scales, so maybe you can get closer. By doing this, now you're able to do better multi-scale processing. And because you're, if you imagine this to be the state of the system itself, you can assimilate into that state. And that's how it enables data assimilation. We did some sort of a simple data integration. We didn't do any Kalman filter or 3D var, 4D var of that manner. All we did was, let's just feed in the input and output and try to figure out what that state should be and use that state to make a prediction. So like initialization of that. And we evaluated that on 17 operational river sites in North Central river forecasting for NOAA. Some of the things we were compared to were the physics-based models, the actual NWS historical forecast, the forecast which actually went to real users. We evaluated that with simple LSTM, LSTM-AR, NR approach. Here's what we saw. If you look at all the sites, pretty much on every metric, we were able to do better than your typical ML-based or physics-based model. Excuse me, on pretty much every metric. And I think the graph is something you should be looking at. So the first thing is models require much longer context to make good predictions. So the whole idea is that if this event has happened before, or something like this has happened before anywhere, the model should be able to learn that behavior and effectively replicate it. So all we are seeing is all the 0 to 7 effectively show the lead time after that for a flooding event, actual flooding event. And the stars correspond to the true observations. LSTM, LSTM-AR, and LSTM-RL are 3 different methods. LSTM and LSTM-AR. LSTM-AR just stands for autoregressive LSTM, so where you just feed in the observations you made back into the model, not really the predictions per se. Then LSTM-RL corresponds to RL. And as you can see, starting from even day 0, our model was pretty much the only one which is able to get the peaks right. And that was consistent across every single lead time. And as you got closer and closer to event, we actually became much more accurate, let's say. And the other thing which is important is that if the situation is changing, the model should be able to quickly assimilate information and correct itself and become better. So for that, let's say all the models are initially off. So all of them are over predicting. All of them are thinking the flood is going to be much more large in this figure 2. But then you make one observation on lead day 1. Somehow our model figures out that what this means to me is that now the flood is over. I have to go down. I have to correct it. And it corrects it much more quickly than others. And as you go to one more lead step, it's pretty much perfect and others are still catching up. Yes, it's eventually catch up, but it's taking time. And that's the time you don't have, especially when you're trying to predict whether the flood is going to end or you're going to have a new event and of that sort. Then we compared it to the actual forecast, which was produced by NWS for all of these floods. So we compared with 12 floods which happened over that decade. And what we realized is for 7 out of 10, without any human intervention, just by machine running on it, was able to beat experts who manually tuned that model for that particular event to make prediction before it goes out to public. Uh, and another avenue forward is what we realized is that an expert can also work on our model to make a better prediction. So that's a path forward, potential path forward. And even without doing that, beyond first 12 hours, even experts are not able to beat what our ML model is producing. So this was effectively just to show that we can assimilate some information. We can in fact effectively retain long-term information through some sort of factorization. So now let's move on to the uncertainty part. So effectively, what we have seen so far is that we have some sort of an encoding, and then you're using that encoding along with a decoder to make prediction. We haven't really talked about uncertainty. So can you do some sort of a structured uncertainty for all of these things because they're important? So one easy way to do this is that you can define a probability distribution of that latent space itself, and then use that to make give you a prediction uncertainty bounds. And that's all we did. So we inferred an entity-specific attribute as distributions over latent space, and effectively then use that distribution along with the decoder to make predictions. An additional advantage of modeling it as a distribution is that now you can do zero-shot predictions. You don't really need these observations. You can just sample from 7 different clusters of something of that sort and just say, okay, this is how this cluster would behave. If this region falls in this cluster, this is how it will behave, and so on. And as for some results, this is just to show some uncertainty bounds. Blue is what we got. Red is what you would have got with a standard deterministic dropout. Sorry, actually, red is what you would have got with Bayes by backprop. And yellow is what you get with a standard dropout. And as you can see, close to peaks, close to whenever it's supposed to go down, it pretty much matches. And it's pretty systematic and regular. The bands are more precise. Better matches true data distributions. So it's increased, more reliable. And another thing is uncertainty increases during high stream flow events, which is how it's supposed to be, because it's context aware. And when you're near high stream flows, which is not something which you have observed regularly in your data, you're probably going to be more certain anyways. Excuse me. The last thing was, okay, we have seen all of these. We have said, okay, you can have an encoder, you can have a decoder, you can include knowledge in different fashions and so on. Can we use all of these to build some sort of a foundation model? So towards that step, I just wanted to define what a foundation model is so that we are not confused. So by foundation model, we mean basically mean any model which aims to learn a generalizable representation from large scale and diverse data, so through some sort of a pretext task. Pretext tasks are usually some sort of pseudo objective, which are artificially designed that enables learning from data that is plentiful, but may not be of high quality or may not have labels. Some of the key capabilities you want from a foundation model after it's built is that it can handle potentially or noisy or unlabeled data for initial training. And it can be specialized for specific tasks through fine-tuning with only limited amount of data, or even run in zero-shot fashion. There's a huge interest in climate and weather foundation models now. These are just some of them in the last 2 years. So the most common pre-training, the most common pre-training task they use is multivariate variable step forecasting without mass reconstruction. So all they say is, I have step 1, step 2's output in time. I want to predict what step 3, step 4 is going to be, and so on. So that's effectively their pre-training task. Some of the downstream tasks they evaluated on things like are forecasting, downscaling, climate projections, and so on, just using the representation they built using the pre-training task. But the problem is many of these foundation models, okay, it's not a problem per se, it's an advantage at this point. Many of these foundation models offer orders of magnitude speed up with similar or better skill over traditional weather models. But they do it in some sort of non-regressive fashion. Again, the same problem exists again. You have difficulties feeding in different types of context. So the question is, can we identify a different pre-training task that is more suited for more wide variety of downstream tasks? So one easy approach there is that pre-training tasks can leverage underlying unknown causal relationships in the data itself. Let's say you do know that there is a variable which causes your variable of interest to change. You can have that along with your traditional variable going into some sort of a black box for now. And if you make an assumption that that variable is better predictable or is available in the future, you can use them together to make eventually a better forecast. So this could be things like, let's say you have a product running at a lower resolution, which you know is reasonably good, but you're not able to do a high resolution prediction of some other product. But if you have both of them in the past, you can build some sort of a relationship between them. And when you go into the future, you can use that low resolution product to just downscale. And we saw that this works through two other papers we have been working on. One of them is now published in ICDM, which I'll be presenting. So it got accepted in that, and so I'll be presenting it in 2 weeks. The other one is a knowledge candidate foundation model we were working on for remote sensing, which also showed that this kind of pre-training is indeed better than a standard pre-training. So I'm just expanding into that ExoTST thing because that's what I worked on with ORNL. So effectively, it's the same thing. So for now, let's just forget about this architecture. More details on the paper because we don't have time. You can just imagine that you have an encoder and a decoder, some input going in. And this time around, what we are trying to say is there are some covariates you have. These covariates are what will determine your eventual output. And this covariates could be things like, okay, you want to know projections under different scenarios, right? Usually. So let's say you have 5 scenarios in mind. So if you know how something happened in past with a particular scenario and its consequence, now you can model them together. And if you have 10 different scenarios in the future, you can make different forecasts for different scenarios in the future. So all you need is those different forecast scenarios and you know those forecast and the response scenarios in the past. First experimental setup, we just tried to see with real data. This is not forecast. So we just imagined, let's just say we have some gold standard observations available in the future. Can our model indeed learn that relationship and use that to make better predictions? So we again tested it on the same kind of FluxNet data set for carbon flux predictions compared to traditional time series approaches. I was able to use that information. And there are other approaches as well, which use that information. For example, this TIE, ED, LSTM, and so on. What we realize is that we can use it better. And we can also use it in scenarios where the data is noisy. So we also realize that our model is more robust to noise. So all of that are in the paper. I'm not going into details here. And the phenomenon was consistent across pretty much every prediction horizon we tried, starting from a short-term time scale of a day to 7 days to 120 days into the future. We also tested it on other standard time series benchmarks because you have to for an ML paper. And there also we saw consistent results. It was pretty much improving on every other baseline which is there for this particular task, or even the baselines which are not built for this task. So what does that tell us? So what it tells us basically now we can use this as a backbone. And we are currently in a process of using this as a backbone to build a time series foundation model. Right now, focusing mostly on land surface stuff, but eventually we are looking to scale it up more. And even in land surface right now, I'm just focusing on technology. Okay, that's all I have for today. Any questions for me?
Hey, thanks a lot for the talk. I have a bit of a technical question because I haven't fully understood how you're implementing the context. I'm sorry, I'm jumping back to this study on GPP where you compared to RICO where you compared with Metaflux, right?
Yeah.
And in principle, what I was wondering is, so if you don't have data for a certain site,
yeah,
how do you make sure that also your context is not just extrapolating, right? I mean, because also your context information can be extrapolating and saying whatever. So then meaning also your context information might not be useful if it's a site that is completely unobserved. But maybe I misunderstood how you.
Okay, actually, you're right. You're saying, what if your context itself was an extrapolated thing? You're not using anything useful. So the whole idea, again, if that is the case, you probably are not going to be able to make a prediction there. So the whole point is, do I have something? It can be noisy. It doesn't have to be perfect. Do I have something which is giving me information which is more than what exists for that site? So even if you do have projections, oftentimes it's probably guided by some principle that's helping you make let's say, okay, for example, in this case, we just use ecoregional climate zone. According to your, effectively, whatever you just said, it's probably a projection, maybe wrong. But the whole idea is that maybe it's close enough. And if it's close enough, it's still better to use it than not to use it. Because when you're not using it, you effectively don't have any information to make that prediction. So even if you do have noisy, you can get close because eventually we are trying to get as close as possible. And our experiments tell us that we can.
Okay, I guess then it would be interesting maybe also to enhance the context there, like
absolutely
include more.
Yeah. And that's exactly why, yeah.
Potentially then also to say, okay, you know, we are out of what we can predict now. Like maybe there's some studies where they basically look at areas of applicability, right?
Yes,
Where
yes, yes,
basically,
yes.
what is the area where we
Okay, so there are two perspectives to look at it. So that's another reason to why model that as a probability distribution. The next one, that way you also tell us effectively tell when you're not certain about that context. And the additional thing is because you have now disentangled, there are a lot more other knowledge guidance you can give. Whatever you know, you can put in to make a better extrapolation. Does that make sense? Or
yeah, it does.
okay.
Thanks a lot.
Are there any questions in the Zoom maybe? Oh, okay.
Hi, thank you. Great talk. What how did like the training like deep learning like had big amount of training data? So I wonder how did you
I cannot hear her. All right. I think I have another mic here.
Thank you. Great, great. It was really great talk. I wonder how did you deal with your training data? Like for deep learning models, sometimes they require a really large amount of data.
Yeah.
So I wonder how did you deal with that problem?
As in, if you have very large data, you're probably going to use either small batch size or you're going to have small batch size, right? Is that what you're asking for? Or I'm trying to understand.
Like like the training data set, like
You mean how do I transform them to a usable ML format? I don't really, the question is not really clear. Can someone explain? Sorry. Do you mean your data is really large? How am I inputting that into model? Is that what you're asking?
yes, like are you training with different data sets?
So, okay, for foundation model? For foundation model initially, right now I'm just training with the different time series data sets. Yeah, the data set is large, it's huge. Yeah, so yes, I'm training with very diverse large scale data set. Not large scale like climate large scale like time series large scale. So it's probably in terabytes. Yes.
Sorry, I will quickly jump not back, but
Yeah.
to the question of the uncertainty quantification.
Yeah.
Have you, I mean, I think it's always nice to see, the uncertainties look more reasonable, right? I mean, it's like a representative
Yes.
check. Is there any way to then properly quantify that? Like
Whether it's correct or not.
calibration, like, I don't know, what do you do with the uncertainties, right? Now that we have some sort of uncertainties. I mean, I'm usually also always careful with dropout as a means to get proper uncertainty quantification.
Yeah, but dropouts aren't really that good. You're effectively doing the Monte Carlo dropout, right? And the bands are not good with Monte Carlo dropouts. They're not uncertain where it's supposed to be uncertain, for example,
Yeah.
like when you don't know what it is.
Yeah, but I understood, for instance, I thought that also in your framework, you're somehow using dropout in order to generate the ensemble.
Have a dropout. So we are effectively modeling that as some sort of a normal distribution. So yes, we do have a bias. We are saying our latent distribution is some normal distribution, and we are sampling from that.
Okay, because I thought that maybe at the start, at some point you said you could basically apply dropout to the context to basically generate.
Oh, okay, that was wrong. Okay, let me explain that. So all we're doing is that, let's say you create a deterministic latent space. We are saying that latent space, let's regularize it by making it closer to a Gaussian and just sample from that Gaussian.
Similar to a variation order.
It's similar to variation. You can convert it to a normalizing flow, do more transformations to make it a more complex distributions, but effectively you're still sampling from a Gaussian.
Okay, gotcha.
Sorry, you might have said this. How do you get the covariance or the variance for those Gaussians?
Initially, we just assume a 0-1 Gaussian.
You just assume.
We just assume a 0-1 Gaussian. We do a K-over divergence to effectively make sure that is a 0-1 Gaussian, close to that. Yeah. Yeah, go ahead. A lot of time.
Have you also looked at basically maybe separating, like, or trying to quantify both sort of the context uncertainty
You mean
plus
allegoric
the
and
predictive uncertainty, like kind of trying to split this and be like, okay, here we're more uncertain because of the context, and here we're more uncertain because of the actual model.
we have not.
Because I mean, you can play around with it, right? You could introduce
You
both
can,
kinds of
yes.
uncertainties.
We have not, and that's actually a good idea. Let me see. It's pretty straightforward to quantify it from a model uncertainty point of view. I'm just trying to see how will you quantify the third uncertainty from context, because you don't really have the real uncertainty for context, right?
That's fair. I mean, you can try to learn some sort of probabilistic, I mean, there are ways, of course, right? You could try to do data augmentation on your context, right? I mean, you can, there are means to.
But
generate
again,
some-
we are dealing with time series data here. There aren't really a lot of techniques to do that for time series. Data augmentation based uncertainty is well explored in images, not so much for time series. Yeah, go ahead.
Thanks.
But it is, I mean, since you're sampling from a Gaussian, that's basically a prior for your own
Exactly,
context
exactly.
uncertainty.
Yeah.
So, but then have you ever done like the inverse step where you observe the time series and you can refine that prior?
No, we have not yet.
Is that like plausible? Is that
I think it is, yes. Yeah. You can have learnable priors. You don't have to put any prior. Priors are also learnable.
okay? I guess in that case, yeah, you'd be refining. You could be pushing your your latent variables to points that were different than what were input.
Exactly. Yes.
Any last questions before we wrap up? If not, then yeah, thanks for the talk again.